Well, thanks for that introduction, Trish. Thanks for the opportunity to come here and tell you about the new cryptographic library that I just finished implementing. I'm going to start out with a poll question just to gauge the audience's familiarity with cryptography. How familiar are you with OpenSSL, encryption, and digital signatures? It's a scalar answer from very experienced to no experience at all. And you know the drill. We'll see the results at the end. So to introduce you to this new cryptographic plugin library, there's been some requests from internal HPCC users and from an external banking customer for a method to encrypt column level, not necessarily an entire data set, but to further protect the data that is considered sensitive. So I was tasked with this mission and created it with, I give you the JIRA number here in case anyone wants to go look at the source code and evaluate my work. But what it does is this is a library that lets you do various cryptographic functions and transformations on data, which I'm going to talk about in just a minute. But I wanted to let you know that it is available in current builds, HPCC systems version 7.4.16, which I'll show you the link at the end of the presentation where you can download it and give it a spin yourself. This new function is part of the Ecl standard library, so it's available to anyone using the Ecl IDE, the command line Ecl, the Ecl Watch Playground, or directly interacting with WS Work units. Okay. So before I jump into the library itself, I just wanted to familiarize you with the types of cryptographic functions that are out there, and then I'm going to dig deeper into what I enable with this new library. At the highest level, there's hashing functions, which is used to verify data. It's not used to encrypt data. As a matter of fact, you typically use a hash with plain text, like let's say an email. What hash does is it transforms a variable length set of data to a fixed size. For instance, one algorithm I'll show you, it always ends up being a 64-character hash. And it's important to note that a hash cannot be reverse engineered back to the original data. And it's also guaranteed that that you won't have a hash collision. If you can't have two different sets of data that compute back to the same hash. And finally, it's fast, and that's going to be important. I'm going to tell you why later on. The next thing is encryption, and there's two different types of encryption. There's symmetric and asymmetric, and I want to go over the difference of those with you. Symmetric encryption uses the same shared key. So the sender of the encryptor of the data and the receiver that decrypts the data, they have to have the same key. If you have it, it's a very fast algorithm, and using symmetric algorithms, you can support the encryption of blocks of data or streaming data. Okay. The alternative to symmetric is asymmetric, and you've certainly all heard of public key algorithms or public key infrastructure, and what those are mathematically associated key files. The public key, is its name implies, is widely distributed, and that's used to encrypt data, and the private key is held typically by just one or two entities, and that's the only that it's closely held and is used to decrypt the data. It's also used to create digital signatures, which is just another form of a hash, which I'll go over that shortly. But just want to point out that this is a relatively slow algorithm. So now we're going to dive into the details of how what we've implemented and the support that we have. So what is a cryptographic hash? It's a mathematical algorithm. It maps a variable length of data to a small fixed size bit string. As I mentioned earlier, it cannot be reversed or inverted. And the way it works is the sender of the data will compute a hash, let's say it's an email, the plain text email, and the hash, and the receiver will use the same algorithm to compute a hash and compare the two. And if they match, then you know the data has not been tampered with and it's trusted. Okay. So what we have here is a sample of Ecl actually using the new cryptographic library. At the top you'll see, and this is a common pattern you'll see throughout the library, is there's a method you can call supported hash algorithms that's going to return to you the names in a set of strings of all the algorithms that we support. At this time, the 5 there are listed that we support. These are trusted algorithms developed by the United States National Security Agency. Probably SHA-256 is the most common one that I've in my experience that I've seen. So if you want to look at the Ecl that follows, this is a simple thing. You import the standard library as always. The next line defines a hashing module called hashing, and the attribute you pass it is the name of the algorithm, which in this case is SHA-256, and what you get is the reference to the hashing module. So the next 2 lines is actually using that module to compute hashes. In this case it's text strings, but you'll notice that it's cast to data, and that's because the hash I allow you to pass data, which means you can do strings, you can do binary data, you can do whatever you want, and what it returns to you is a data type of a hash, and that's what you send out, and in this case it just outputs it to the work unit. But the point here is that we strove to come up with a simple interface. If you've ever programmed using OpenSSL, it's very complex and very intimidating, and so what we wanted to expose to the Ecl users is something that's quick and simple and makes sense, and this is an example of that, I hope. The next thing I want to talk about is symmetric encryption, which, as I alluded to earlier, and if you look at the diagram, uses the same key. The sender and the receiver each has the same key. The sender encrypts the data using that key, sends the data, and the receiver uses that same key to decrypt the data. The key management is a topic here of interest. It's important that the key is protected, because anyone who has the key then can intercept the data, modify it, decrypt it, do all sorts of bad things. So that's one of the common topics in encryption, is how do you manage the safety of the key, and that's something I can't really tell you how to do. There's all sorts of different ways out there which you can use, but I want to show you now an example of using it. It looks very similar to what you saw before. There's a method you can call to get the supported algorithms, and in this case we support 3, AES 128, 192, and 256. The difference between all these algorithms, as you might guess, is the speed at which they compute the encrypted data, and also the complexity of how hard it is to crack it. So as before, you import your standard library, and then you define a symmetric encryption module. The attributes that you're going to pass it are the algorithm name, which was returned from the call above, and a passphrase. And each algorithm has some restrictions on the passphrase, that the length of it, the complexity of it, and that's not something we control. That's up to the control of the algorithm, so you have to look that up to understand the size of each. But anyway, once you've created this encryption module, then you just call the encrypt method on it to encrypt data. As before, the type that it accepts is a data, not just a string, so you can encrypt anything, and it returns a data object with the encrypted data in it. And then if you'll see in this example, I just immediately pass that encrypted data to the decrypt method and assert that they're the same. And again, the interface, we strove to make it as simple as possible, not intimidating to the Ecl user, and it's that simple. Okay, now I want to talk about asymmetric encryption, and as I alluded to earlier, this uses public and private key pairs. As you'll see in the graphic, the encryptor uses a public key to encrypt the data and send it over the wire. The receiver, which holds the private key, uses it to decrypt the data back into plain text or to the data, whatever format it was in originally. This is known as public key cryptography. You've probably seen PKI, which is public key infrastructure. There's numerous three-letter acronyms floating around, but as I said, it has asymmetric pairs of keys to encrypt and decrypt. You can generate these keys yourself. There's OpenSSL utilities, command line utilities, where you can generate them, or you can send a request to a certificate authority to send a more secure and verifiable public and private keys. And as I said, the public key can be widely distributed to anyone. It's used to encrypt the data, and the private key you want to keep tightly held because it's the one who can decrypt the secrets. Of interest here is that it's slower than symmetric encryption and decryption. So of note, if you've ever used SSL or transport layer security, the way it works is it uses public and private keys. So once they use those public and private keys, which like I said is slower, to establish a secure channel, then what they do is dynamically generate their own symmetric key and exchange that over the channel, and then further communications on that channel uses symmetric, which is the faster. That's just an interesting thing I found while I was researching this. So again, this should be starting to look familiar to you. There's a Ecl call to make that returns a set of strings of all the supported public key algorithms. And at this point, RSA is the only one that we support. And the next two lines, what I want to demonstrate here is that there's two ways to define the module to do public key encryption. You'll see the difference is, one, you can pass it key file names for the public and private key. This is a file system specification that will have to exist on the nodes, and we'll go out and open the file, read it in, and use it to perform the public key functions. The other one takes the keys as a buffer, so your Ecl could stream it in from some other source and then pass it on to create these modules, which then use it to perform the functions. So the Ecl example that you see below, as always, import your standard library and define your public key encryptor module. The attributes that you pass to it are the algorithm name, of course, and in this case I took the public and private key buffers and a passphrase, and that defines the module that you then subsequently call iteratively or whatever your needs are to encrypt the data. And again, all you pass is the data, and if it's string, you have to cast it to data. And in this example, I encrypt it, then I immediately decrypt it, and then just output the decrypted string. And that's it. It's easy to use as that. Finally, I want to talk about digital signatures. A digital signature is just a hash, which we talked about before. In this case, though, it's computed with public and private keys. Again, the intent of a hash is meant to verify that your data has not been tampered with or massaged, but instead of using the simple algorithms as before, this is more secure in that it uses public and private keys. It is going to be slower than a hash, but it's more secure. And again, the sender of the data will compute that signature, send the signature with the plain text data, and the receiver will recompute the signature with that plain text data and then compare the two signatures, ensuring that they're the same. And of course, if the hash doesn't match, or the signature doesn't match, then you know the data's been tampered with and it's unreliable. So for my final Ecl example, I show you again, you saw this before, the supported public key algorithms. As I said, the digital signatures and public key encryption and decryption both use the same module. So again, as before, you have two different ways of defining the module, from a file spec or from a buffer. And what you'll see in my example here is I create the module as before. And to sign the data, you just pass the data. In this case, it says, please grant Bob 1 Bitcoin. And then to verify the signature, you pass that signature and the original plain text, which in this case has been tampered with. It says, grant Bob 5 Bitcoins. So the assertion below says that it should have returned false. And that's all a digital signature is. So in conclusion, this library is in its infancy. It is available now, and I hope you guys will get your hands on it and start to use it and give me some feedback. You can download it from the HPCC systems build 7.16 and newer from the link below. The goal over time is to add new algorithms, add new cryptographic features, functions, enhancements. And I do want to mention the documentation will be available in the library user's guide, and also I believe the Ecl IDE. But give it a shout, give it a try, and reach out to me directly with comments, or you can open a JIRA or post comments on the HPCC systems forum, whatever method you prefer. And finally, if you want to talk about it or any other platform topic, if you're going to be at the HPCC systems October 16th, the platform team will be hosting what's called a platform expert lab, which there'll be details given at the conference, but we'll be at table 550, and I encourage you to come by and just meet us, tell us what you think, give us some ideas, ask any questions, or talk about any problems you have, whatever. Love to meet you all. And real quick, I just wanted to acknowledge that I didn't do this all by myself. Dan Camper helped me with the Ecl interface design, which is an area that I'm not that familiar with. We came up with a really clean interface. Jim DeFabia, he knows everything about the HPCC systems platform. He helped me with integrating in the standard library, and he came up with some really good code samples, which I hope you look at in the documentation. It shows you how to stream in public and private keys and all sorts of other things. And as always, Gavin Halliday and Jake Smith, who reviewed my code, made sure I kept it clean, gave me ideas on how to optimize it, and just basically helped me make it a better library. So finally, I want to have a follow-up poll question. Do you feel it's useful to encrypt sensitive data columns even when the data set itself is encrypted? And of course, we'll go over that at the end. So, Tricia, let me hand it back to you.
Okay. Thanks, Russ. You know, I think it's great to have this security feature now available to the community to leverage. So there are some questions waiting for you as well. So while you take time to review and prioritize those, let me go over your first poll results. And the question was, how familiar are you with OpenSSL, encryption, and digital signatures? And 75% have some exposure, so while 25% have not. So again, a suitable topic, I think, for this audience. So let's go on to the questions. Are you ready?
Yes.
All righty. Got quite a few in here. So first up, how do you provide key file contents and passphrases without encoding them in Ecl?
So yeah, this is really an Ecl question. Obviously, you don't want to hard code private key files and passwords in your Ecl. So you would need some kind of external store. There's different ways that you can do it, but some type of library where you can externalize these things and read them in through Ecl. And I know I'm being a little vague, but if you look at the documentation that's coming out, we show one or more ways of doing that without having to expose it in Ecl code. You theoretically could put a public key file in your Ecl code, but that's, over time they expire as well, so it would not be a good idea. So as I alluded to earlier, key management is a hot topic, and that would take some time to think something like that through.
Yep. Okay. All right. Next up, how would you decide which of the supported cryptographic algorithms to use?
So each one has its own characteristics. Generally, the more secure they are, the slower they're going to be. So depending on the sensitivity of the data, and you'd have to do some modeling to see, the performance hits that you take by selecting one over another. But you want to choose the one that's going to most be appropriate for the sensitivity of the data that you're protecting.
Yeah, that makes sense. And then how would a cryptographic hash be useful in an Ecl data set?
So to me, what I see is, like I said, a hash is always going to be a fixed size. So if you have a large piece of data that you're indexing over, what you could do is create hashes of that data. And because a hash is guaranteed to be unique without collision, you could use the hash as your search key. So when you want to search for something, you can compute a hash on the fly and then look up using the hash or a digital signature.
Yep. Okay. Thank you. And then I think the examples that you gave in your presentation with the Ecl code will be very, very helpful. Okay. And then one last. Yeah. Go ahead.
I was just going to say we tried to make the interface as easy as possible because it can be very intimidating if you're using the native libraries.
Well, I think in general, at least to me, security is an intimidating topic as it is. So I'll take all the help that you want to throw our way. One last question before we wrap things up, Russ. Is there a simple supported way to support hashing particular fields in a data set, or do I need to write a project with a transform to perform that hashtag?
This one is beyond me. I would have to defer to some of our Ecl experts, but I'm certain there is a way to do it. I could ask someone else and get an answer for you.
Okay, that'll be good, and we can always provide that afterward. So thank you for answering those questions, Russ. And your last poll to the audience was, do you feel it is useful to encrypt sensitive data columns even when the data set is encrypted? And the results were, go back to that. Everybody's waiting. Drum roll. 100% said yes, so not obvious. So that is a good to see that our audience thinks an extra layer of security is always useful to have. So thanks again, Russ.